Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to introduce Professor Josep Torrellas from the University of Illinois today. Josep is a very well-known, distinguished, and senior member of our community. He's an IEEE fellow. He received his PhD from Stanford in the early 90s, and he's done seminal work in speculative multi-threaded architectures, processor and memory architectures, and debuggability and programmable, reliable architectures. And his new work looks at bulk sequential consistency and is really exciting stuff that's going to help us to tackle the parallelism problem. So I'd like to thank Josep for coming and sharing his most recent work with us today, and it's a real pleasure to have him here. I will. We don't want that vicious Pacific Northwest sun burning you as you give your talk.
Very good. Thank you very much. Thank you very much, Doug. I'm very pleased to be here. Thank you for hosting the visit. Thank you to all the attendees. You know, we're small and cozy here. Hopefully you'll find some of this work interesting and useful. The work I'm going to present is a big project that I have with my students on designing the new multi-core architecture of the future, hardware and software, with a big emphasis on programmability. Many people contributed to this work who are not at Illinois anymore. These are some of my students who contributed to this work. In particular, you'll see a lot of work by Louis Sezzi and James Stuck. So the project is called the Bulk Multicore for Programmability. Let me and by the way, please stop me anytime if I say something wrong and it doesn't make sense, okay? And you know, I'd like to have a discussion rather than just a simple talk. Let me start with what I think are the challenges that we are facing as we move towards the multi-core era. The first one is probably in the minds of everybody here is 100 cores per chip are coming and there's preciously little parallel software, okay? Certainly at the client side, which means that for system architects, both hardware and software, our main priority has to be to design a system that supports a programmable environment. Okay, of course, this is very cheap to say, but what does it mean? User-friendly, the most user-friendly concurrency and consistency models that we know of, we should be supporting them efficiently. And also, I think this is very important, provide an always-on production-run debugging environment, because most of the people who will be using these machines are not going to be experts, so we need to help them a lot. Hold their hands a lot. Another challenge that I see is that decreasing transistor sizes are making designing cores harder and harder. The reason for this is that as you decrease the feature size, there are more and more design rules that you need to support, which means that if you want to satisfy them manually, it's getting harder and harder, which means there'll be this tendency of taking the core and to some extent shrinking it. Which means that, in my opinion, cores are becoming commodity more and more. There'll be big cores, small cores, and specialized cores. And the innovation and the value added of the chips will be mostly in the cache hierarchy, network, power management, and so forth. I think this is an opportunity for us because designers are going to be, I think, willing to put this extra support, and certainly able because there's enough silicon. You'll see in the design of the bulk multicore why this is important. Another issue is that we will be adding accelerators. This is something that we see coming. And really, we're going to see that these accelerators want to have fine-grained sharing with the main cores, which means that the accelerators will need to have, ideally, the same simple interface to the cache-coherent fabric as the main processors. Okay? Which means that if we want to exploit them, we're going to need to have, in my opinion, simple memory consistency models. So in this context, let me give you a brief overview of a kind of a possible vision of the multi-core of 7 to 10 years from now. 128 plus cores per chip. Since people will be providing shared memory programming models, what we need for the hardware is to support shared memory. Certainly I will support shared memory, perhaps the whole chip, perhaps groups of processors, islands of processors there. Certainly, we can have hardware that enforces the interleaving restrictions imposed by the language and the concurrency model. Both the hardware and the language and concurrency model will have to be designed together. And I will make the case for sequential memory consistency. Certainly, we are able to provide hardware to support this at a very reasonable cost. At the same time, a sophisticated, always-on debugging environment that can be on all the time, even for production runs. And this has many components, and some of them dear and near to the work done here. The deterministic replay of parallel programs. We can do it with practically no log at all. Data race detection. We can do it at production run speeds with very little slowdown. And pervasive program monitoring, as I will discuss. So with this context, then, this talk is about the bulk multicore. Okay? We even have a picture of the bulk multicore. So what's the main idea of the bulk multicore? It's very simple. Let's say that we eliminate the ability to commit individual instructions at a time. Okay? And we don't provide architectural state after every single instruction. This was a fundamental assumption, is a fundamental assumption of current processors. Current processors, you execute out of order, but instructions commit in order, and after every instruction, you got to be able to provide the architectural state to the rest of the machine. So as we move to multiprocessors, this becomes harder and harder, and this is the root of all the problems of memory consistency. Okay? Loads and stores now take a long while, and you have many outstanding, and while this happens, something else may be messed up. And because you want to keep this in-between instruction architectural state, then you have to worry about memory consistency models, stalls, ordering, overlaps, and so on. Let's say we just get rid of this. And instead, what we have is processors only commit chunks of instructions at a time. Okay? Say, for example, 2,000 dynamic instructions. The key word here is dynamic instructions. Okay? This is not something that is visible to the software. Okay? The processor, you give a thread to a processor, the processor executes, starts executing 2,000 instructions, say, and then it says, okay, now it's time for me to make the state visible, and if somebody wants, here's my architectural state. Then I continue executing 2,000 instructions and so forth. So that's the idea.
What if there's synchronization operations in there?
Doesn't matter. In fact, you'll see that the sync becomes a no-op. A fence becomes a no-op. Synchronization will still work, except that you're not going to know where inside this chunk the synchronization occurs. Okay, so that's the idea. Chunks execute atomically and in isolation. Okay? People know what this means, but just to make sure, atomically means that nothing that I do within these 2,000 instructions will be visible to the rest of the world until the end. So if there is a lock, if you grab a lock, nobody's going to see that you grab the lock until the end, when you make the state visible. Or if you release a lock, same thing. Isolation means that while you're executing this chunk, the machine state cannot change on you. Which means that if you're executing a chunk and you read a value, and while you're executing the chunk, somebody else writes to it and commits, you got to get squashed. You just cannot have this thing execute. Atomic isolation, and we'll use, at the basic level, buffering of the state of a chunk, and if you have to squash, undo. But most importantly, we're going to use something called the hardware signatures, which is a very simple hardware primitive that will enable efficient execution atomic and in isolation. Now, if this sounds familiar to you, this seems like transactional memory. It's not the same. It's quite different. You could think of this as being transactions all the time in hardware, invisible to the software. So this doesn't say anything about the software. You can have object-oriented programs on top. You can have functional programming, anything you want. This is invisible to the software. Okay? It's just a way, as you will see, to execute efficiently. And it's not a way to parallelize programs either. Okay? What I do here is I give a thread to a processor. Okay? You have multiple, say, take a parallel program. I give a thread to each processor, and each processor will chunk it to execute efficiently. And this should work with synchronization. Okay? It should work with logs, barriers. It works. You will see that the advantages of a current processor is that you improve the programmability quite significantly, higher performance at current processors, and simpler hardware. If this seems too good to be true, maybe you can wait until I say some of these things, and then you can argue with me if you don't agree. Okay? So that's what I will do in the rest of the talk. Try to convince you that if we just get rid of that thing, that is kind of a fundamental tenet of current processors, we get these three, and we don't need anything else.
So to go back to Rich's synchronization point, can you address how you handle something like a swap instruction that has read, modify, write semantics?
Oh, that's fine. That's fine. You will do that if two processors do this. Okay, only one will succeed, right? When will they succeed? The first one that commits the chunk.
Right. So you're basically saying that a swap instruction, anything that has atomic semantics to memory is going to, in some sense, be cached until commit.
Yes, yes. Everything is cached until commit, as you will see. This works with logs, barriers, whatever. The only difference is that a chunk now may have spins, right? Mm-hmm. So useless instructions, you're spinning longer. So if the guy who releases the log doesn't release it until after, at the end of the chunk, that guy may spin longer. Or you may have squashes. Rich?
I was going to say, it seems very optimistic, and I was just wondering how well it's going to work if you have a lot of contention.
Okay, so the high-level idea is the finer the grain the sharing, the more squashes you will have. Think about it. The way this works is that if you want a program that works like this, right? This guy said something, this one reads, this one sets. You're not going to get that. You're going to get either this or this. And what you will have is spinning in these other chunks, okay, or squashes. But I want to live with this. I want to live in an environment where if you have fine grain, you're going to reduce the chunk size, right? If you have coarser grain, you move to bigger chunks because it's much more efficient and has this thing.
So will the chunk size change dynamically then?
You could. In this case, we don't do, but you could do that. So currently, we just use 2,000 dynamic instructions, right? But if you find a lot of squashing, you could dynamically reduce it.
Are you going to talk about exceptions in I/O?
I can very simply say what the idea is.
Yeah, that'd be great.
So I'll get to it in a second. Okay? So let me just go over this first. So in the rest of the talk, I will explain what the bulk multicore is, how it improves programmability, and then revisit the vision of the multicore. So very briefly, how does this work? So something called hardware signatures. What's the idea? Imagine that every time a load or store retires from the reorder buffer, right? There is hardware that takes the address that you're loading from or storing to and automatically and transparently hash encodes it into a signature. Okay? So something like this. Take the address, you do some permutation, and then you hash it into here. You set multiple bits for a given address. Okay? Another load and store, you do the same thing. Okay? So this is a Bloom filter, really. This signature collects kind of a footprint of what addresses you've read or written. Okay? You have a read signature and the write signature. Okay? All the reads go to one place, all the writes go into one place. And you have this that summarizes the footprint of a chunk. So each chunk has a read signature and a write signature. Again, transparent to the software. Software doesn't see the signatures. Suppose at the same time that in the cache hierarchy of the processor, close to the L1, not in the core, but in the cache hierarchy, I have very simple functional units that operate very efficiently with the signatures. Okay? Suppose I have a bunch of AND gates that take the intersection of two signatures. Right? So this thing now will contain the addresses that are common, or a kind of an encoding of the addresses that are common to both signatures. Right? I can check if this is 0 by a bunch of AND gates and NAND gate. If any of these subfields is 0, I know that this signature is empty, which means that there is no intersection between these two chunks. I can have membership. Is this address part of the signature? Well, I take the address, I use the previous picture to encode it into a signature, then I intersect the signatures using this, test with 0, and that tells me if this address could be in the signature or not. Okay? So what I have here is an efficient way of operating on groups of addresses. Okay? Very efficient, low overhead. Okay? There's some false positives, but it's very efficient. If I have this, then atomic and isolation execution becomes trivial. Okay? So here's how it works. Suppose I have two threads, two parallel threads, right? As I execute, this guy is issue loads and stores. Because I want this to be atomic, I don't let this store seen outside. Everything that I do is buffered in the cache, right? I don't send invalidations or anything, but the hardware automatically generates a write signature and a read signature for this chunk, right? At the same time, this other processor executes its own chunk. As it loads data, it loads the correct data. Remember, it cannot load this store here because it's invisible to it. It reads the correct data. It generates its signatures. Now, what does it mean to execute atomically? When this guy wants to commit, all it needs to do is it needs to send the right signature to this other guy. And then clear its own read and write signature. Everything is done. He has committed. Does it make sense? So commit simply means sending the signature to everybody else, okay, in this case the other processor, and clearing your own signatures. Suddenly, the data that you have in the caches becomes visible to the rest of the world. You don't write back all the data. No. The signatures itself should be enough to set the whole system consistent. Okay? So that's atomic execution. Isolation. In the cache hierarchy of this processor, the signature comes in, and in this functional units in hardware, there is the intersection against its own read and its own write signature. Okay? In this case, what you can see is that this thing will be null, but this is not null, because this guy stored B, this guy loaded B, therefore this guy will get squashed. So if this thing is not null, then this guy has to be squashed if I want isolation. So with this support, then I have atomicity and isolation.
So are you required to broadcast the write mask to all participating processors? So do you scale as n squared in terms of your overhead?
Okay, so what I would do is I will not actually broadcast it. In a bus, you just put the signatures on the bus, everybody would see it. In reality, you would have an arbiter that is connected with a directory. You would send it to the arbiter, and the arbiter will say, all this works with cache coherence, by the way. The signatures are enough. So then it says, oh, I know that only processors 10 and 16 are interested in this particular, in the data that could be in the signature. And then this thing gets only forwarded to those guys. So the basics of bulk multicore is the combination of chunk operation and signatures. So we execute, as I said, each chunk atomically in isolation. So like this, right? There is a distributed arbiter, okay, that ensures a total order of chunk commit. So you don't send it really to the processors. You send it to the arbiter. The arbiter very quickly detects whether you can commit. And if so, it says, okay, you're committed. Then you can clear the signatures. Okay? And in parallel, it will change the state of the directories and so on. Okay? So it is really what happens is that we have a certain set of interleavings, not all of them, of course, but a set of interleavings as if we had this guy selecting a chunk from each processor. Okay? Now, if you have atomic execution, isolation, and you have total orderings, then you have sequential consistency at the chunk level, right? And if you have sequential consistency at the chunk level, you have it by definition at the instruction level. So now you have sequential consistency in this machine. Okay? You don't allow all possible interleavings, but you have some interleavings that are legal, right? And because I choose the size of this so that the overhead of commit and so on is small, I have high performance. So the key is you support sequential consistency with low hardware complexity and high performance. Okay? Why do I say low hardware complexity? Now, in current processors, to support sequential consistency, you have to live with the reorderings of loads and stores. So current processor, you issue a load, and from the time the load is issued until it retires, there's this window of vulnerability. You have to watch for incoming invalidations in current processors to support sequential consistency or any model that allows you to do speculative work. Now, whenever you have an invalidation on the bus, it has to be snooped up all the way to the load buffer of the current processors. Okay? So that's an intrusive effect of consistency into the core itself. Moreover, you cannot displace anything from the cache. Okay? If you displace something from the cache, then you could miss an invalidation coming in. Therefore, if you either displace something from the cache, the processors nuke the load and all the successors. If an incoming invalidation snoops in the load store queue and finds a hit, you have to nuke the load and all the successors. Okay? What I'm proposing here is ignore all the stuff. Okay? Let the loads and stores execute out of order as long as they make it to the signature, which is in the cache hierarchy, and then at its due course, the signature will commit. Okay? And if in the meantime somebody else sends you a signature, then that signature you intersect, you get squashed. So either everything or nothing. You can see that we have moved all the complexity away from the core into the cache hierarchy.
I don't see how you can, I guess I don't understand how you can recover the processors that you need. I mean, the Bloom filter encodes the read and write sets into an approximate hardware hash. And you can't recover which cache lines were read to or written from.
Okay.
Right? So you lose information. And so, if you don't, it's highly probable that these future, if we get to 128 cores, we're not going to have a central bus. We'll have a directory out of the L2. So how do you convert those signatures into an invalidation or a squash messages?
Very good. So from the signatures, you have to be able to generate a superset, a safe superset of things that you want to either invalidate or squash, correct?
Yep.
All right. So I showed you a bunch of functional units that operate on signatures before. Mm-hmm. There is one that we call expansion. And expansion generates a conservative set of cache sets that can contain data that belongs to the signature.
Right. It's a superset.
Superset. So all you need to do is to ensure that this function cannot squash or cannot invalidate any data that you shouldn't do for correctness. Okay? But if you invalidate something and at most you're going to have a miss on that thing.
If you assume that a load or a store has to bring the cache line into a processor before it can operate on it, then in the then at the directory you can say, let me generate a set of all possible cache lines that could intersect with the signature, and any processor which is caching that line needs to be squashed.
Well, so not squashed. Okay. So first of all, when a processor receives a signature, you do two operations. Okay. First thing is you intersect the signatures to see if you need to squash the chunk.
That's assuming that you're broadcasting the signatures.
No, it doesn't matter. If you send it to a processor, suppose you send it to a processor. Okay, the processor receives the signature. First thing you need to know is, one, do I need to squash this guy? You do the intersection with your read and write, and if it says yes, I need to squash this one, then what you do is you squash the thread, and then you use that thread's write signature to figure out what are the dirty lines in its cache that need to be invalidated. Because when you squash a thread, I see. So you have this expansion using your own write signature, and you invalidate this.
It's a local operation.
Yeah. So in addition, irrespective of whether you get squashed or not, okay, when you receive a signature, okay, you need to invalidate from your cache any lines that guy could have written, simply because they become stale, right? So you get the signature, and then you apply a second expansion on the incoming write signature, and you invalidate from the cache those lines. Yep. So there's two operations. One you always do, the second one only if you squash the thread.
So I misunderstood you earlier. I thought you were talking about using the coherence protocol to prevent a broadcast of your write set.
You do. You do also.
All processors.
You do. Whenever you send the signature to the arbiter expands this in the directory in the same idea, figuring out what are the possible lines it maps to. Then for each line, it knows what are the processes that contain data.
Right.
And it sends the signature only to those. Right? So you always have to design the system to be on the conservative side. You cannot miss anybody, but if you invalidate something that is clean in a cache, maybe okay.
Are you going to show us results for a large number of cores about what fraction of lines get what fraction of the cores a signature gets expanded to effect?
This talk doesn't have any data at all.
Thank you.
So that's one thing. Second is high performance. This is important because one could design it with very low complexity, sequential consistency, and have poor performance. Not so, because instructions within a chunk are fully reordered in hardware. In fact, loads and stores are reordered in any way you want inside a chunk. If you have a fence, that fence is a no-op, because the fence is there in the chunk to prevent instructions that are after the fence from being reordered before the fence. Here, because nobody's going to see anything in the chunk anyway, you can reorder anything, ignore the fences. In fact, I will even show that within a chunk you can issue accesses from two different chunks within a thread, okay? As long as each chunk has its own signatures and the chunks commit in order. But you can have requests from different chunks out of order within a thread. So, to summarize then what we're discussing here, the gains of this machine is in simplicity, performance, and programmability. Why that? Hardware simplicity. You can see, oops, sorry. For some reason this thing went back. Okay, so hardware simplicity. The memory consistency support is moved away from the core. I could design a core without worrying about whether it's going to be, has to support x86 consistency or PowerPC consistency. It doesn't matter. Give me a core, reorder the loads and stores you want. As long as you have signatures and it works with chunks, then the memory, the cache hierarchy will take care of the consistency. Okay? And it will do support sequential consistency. Okay? So designers don't have to worry about this. So that's good because we move towards commodity cores. You take a core, do anything you want, it's going to work in your system. Because now we have it in the cache hierarchy. Same thing for accelerators. Suppose I want to put an accelerator that works very well with fine-grained sharing with graphics or whatever. Do I need to worry about, this is going to be for an x86 machine, so I need to worry about fences. I need to worry. No. Here, give me what you want, do any reordering you want, as long as it has chunks, okay? As long as it works with chunks, does fences, reorder another fence, it works. High performance, as I said, fully reordering intra and intra chunk. Okay? Now what about programmability? All this, as I said, is invisible to the software. Okay? That's the first level. You can have any language, any programming model, anything you want is fine, because that's under the covers.
Sorry, Joseph, that's the only exception I can think of is if you've got a read to an I/O device that has side effects.
Okay, so now what happens if you have I/O? Now it's a good time to do this. I/O and speculation don't like each other very well, right? So whenever you have to have an I/O, you have to commit the chunk.
Yep.
Then do the I/O, then start a new chunk.
Right.
Okay, so that's forced cutting things. Exceptions, not necessary, okay? As long as you can roll back this thing here.
Yep.
Okay, so similar to what transactional memory to some extent. Now, support sequential consistency. I argue with low hardware overhead and high performance. Why is this useful? Okay, so why is this useful? Jim may disagree or not here, but let's see. I think that the main reason why this may be useful is that many correctness tools will assume sequential consistency. Okay, so as we move forward to an environment where all the machines will be parallel, one would expect there will be more and more parallel software. Many tools will appear, hopefully, that will say, I can prove that this is correct, but you have to have it in sequential consistency. Now, these tools, some of them exist today. If you run this code, the subroutine that you proved correct in a machine that supports x86 consistency, then maybe it's not going to work. It would be nice to have a machine that whatever you prove is correct, is correct. Okay? I'll get to this a bit more later. Second important thing is that it enables novel, always-on debugging techniques. What is the insight here is that because we only keep per chunk state, okay, we don't keep load and store information anymore. you can cut down on a lot of the state that tools need to support now. Okay? So this means that deterministic replay of parallel programs, as I will discuss, you don't need to worry about this load happened here, this store arrows. Only you need to know is chunks. Okay? So we'll see that we can eliminate the whole log, actually. Another one is data race detections. Right? So here we're going to have to cut at sync points. This is the only exception as far as programming effects is concerned, software effect. But if you do that, then you only need to worry about chunks, stuff within a synchronization block, between synchronization points. And then there's something else, if I have time, I want to talk about, which is the next step. What if I make these signatures visible to the software? Okay, so far I say the signatures are not visible. What if they are? Then I can do lots of fancy stuff that have to do with watching addresses, okay, pervasive monitoring for debugging, and even novel compiler optimizations like disambiguating ranges of addresses automatically.
You'll also introduce loads of new wonderful side channel attacks.
Sorry?
You'll also introduce wonderful new side channel attacks for any of these chunks that are running cryptographic operations.
If you make the signatures available, you mean?
Yeah.
Yes, so that's an issue, right? You'll have to do it in a way that you're always, okay, so I cannot give you an opinion on the security and attacks, but certainly you could mess up things and not doing it very efficiently.
Maybe a privileged operation.
Probably not, you don't want to do it. Anyway, so many.
I would quote Benjamin Franklin, those that would give up liberty for a little security deserve neither.
Okay.
So what does that mean?
Huh? And I think that you could think of many new tools that gives you new functionality thanks to having these signatures visible. But let me just go over these programmability issues first and then just conclude the talk. All right, so this issue of sequential consistency, as I said before, formal verification tools hopefully will become more and more pervasive, and they like to have sequential consistency, otherwise the state explodes. Another thing is that there's all these issues about semantics whenever you have data races. Okay? Well, if you have sequential consistency, all these discussions of what is the semantics whenever you have data races, what is the Java model, so on, all this disappears because it's very clear what a data race does in a sequentially consistent machine. Okay? So especially for safe languages, all the stuff disappears. Another thing is that it's much easier to debug parallel codes, of course. Try to debug a parallel code that has a kind of a subtle data race problem in a sequentially consistent machine and one that is not. So that's kind of another main reason. And finally, as Jim Laros always tells me, there are some guys who always want to use handcrafted synchronization, and of course they don't like to have unexpected results, right? And having sequential consistency would help. Anyway, so here's a machine that could support this with low cost. Now let's look at some of the tools that are enabled by working on chunks. Okay? One is deterministic replay of parallel programs very efficiently. So what is deterministic replay? So during execution, I want to run a parallel program such that the hardware in parallel records into a log the order of dependencies that existed in these threads. Okay? So I run the code, and then I have this hardware that logs all the dependencies. The log, in a sense, has captured the interleaving of the threads, right? And so then when I replay the code, I simply re-execute the program, enforcing the dependence orders that I have encoded in the log. Okay? So that's the idea of deterministic replay of parallel programs.
Here, do you really mean you're recording the order in which the chunks are committed?
Well, I'll get to it, but this is the general idea. The general idea is you kind of have to record the interleaving of the threads, right? So in conventional schemes, what you have is you have arrows, dependencies between threads. So in here it says, in instruction N1, processor P1 wrote to A, and in instruction M1, processor 2 read A. So there's this arrow. If I observe this in the initial execution, then the log of processor P2 has to have an entry that says, when I get to M1, I have to stall until P1 has finished N1. Okay? So I have an entry for each of these arrows, and that encodes what happened in the original execution. Of course, people have come up with very fancy ways of combining arrows so that you have fewer entries. But this is what you need, and potentially have very large logs, okay? Because you need to worry about all the dependencies. Now, if you have bulk, then the log that is necessary becomes minuscule. Okay? During execution, I don't worry about dependencies. I just do chunks, right? So basically, if I have a bunch of arrows that go from this guy to this guy, and this is a chunk and this is another chunk, okay, I don't need to store these arrows. All I need to store is the order of chunks, right? So my log then is the log of all the processes together, not just of processor 2, is simply the history of chunk commits. Okay? Chunk from P1, then P2, Pi, and so forth. Right? So that cuts the log an order of magnitude, approximately. However, I can be even smarter now. I could say, what if the arbiter, the one that takes the chunks from different processors, has a built-in algorithm, okay, and says, I'm going to take a chunk round robin, a chunk from this guy, a chunk from this one, from this one, from this one. Okay? Of course, I'm going to pay with some performance overhead because I may have load imbalance. Okay? The process that is its turn to commit may not have the chunk done. Okay? But if I do this, say I fix the chunk commit interleaving, then I have completely eliminated the log. There is no log necessary because the arbiter knows when it replays the code, okay, it will say, okay, everybody execute, and I'm going to take this chunk first, then this one, this one, this one, and so forth. So what you could do is, you could, whenever you start debugging a program, right, use this mode, okay, to find many bugs. You may have to run for a day to find the bug. Once you find the bug, you deterministically replay it, and you fix it. And once you've fixed most of the bugs, then you can move to the other mode where you have a bigger log. Okay? Does it make sense? If you think about it, what I'm doing here is I'm limiting the interleavings that are possible, right? Certainly at the fundamental level, chunk already limits some of the interleavings. Okay? These are the only possible, this is one of the possible interleavings. Okay? At the cost, so I limit the interleavings, no performance cost largely at the beginning, and I get small log. This has a performance cost, but it eliminates the log completely. So that's one example that what's possible. Another one is if you want to detect data races. Here what I would do is I would cut the chunks at sync points. Okay? So suppose I have the synchronizations like this, logs and so forth. Then I would cut the chunk every time there is a synchronization operation. Okay? Now, then I assign an ID to each of these chunks, okay, that follows the happens before. So the ID of this guy is a successor of this guy, which is a successor of the other guy. Within a thread, it's clear. Across threads, I use the synchronization operations to order chunks. So this guy has to be a successor of this one here. The guy that releases the log has to be a predecessor of the one that acquires the logs next. Okay, so how is this done? You augment the software data structure of the lock to have an extra field that specifies an ID. When a chunk is about to release the lock, it stores its own ID into the software structure. Then the next chunk that grabs the lock, after grabbing the lock, it reads this ID and it sets itself to be a successor of this guy. Okay? So this guy's ID is a successor of both this one here and its own predecessor in the same thread. So you have a partial order of chunks, basically, right? Because of transitivity, this chunk now is a successor of this one up here. Okay, so this guy is a successor, but this guy here is not a successor of this guy here. So how do I detect data races? Okay, so what I do is, when I detect communication between chunks, I can use signatures to detect that, okay, or I could use plain loads and stores, but let's say I use signatures. Then if I see an intersection, I see that these two guys have communicated. Then if this, I compare the IDs. If the IDs are ordered, it means that there's a synchronization in between these two chunks, and therefore there's not a data race. While if these chunks are unordered, then I found a data race between these two chunks. Right? Question there will be, what exactly is the request that caused the data race? So there's some stuff to do. If you work with signatures, you may have some false positives. Okay? And you have to do some extra work. But that's the idea. All the references inside or between two synchronizations belong to the same equivalence class, and I can treat them together. Okay? I can do the same thing for flags and for barriers. In case of barriers, all the successor chunks in all the threads become successors of all the chunks that led to the barrier. Make sense? All right, so now I'm ready to get to the final part, and that is, what if we make the signatures visible to the software, okay, through the ISA? And I claim here that you can have pervasive monitoring, okay, you support numerous watch points and so on, or you can have novel compiler optimizations, such as I'll show you, code motion and so forth. Okay. So let's look at the two things one at a time: the monitoring abilities and the code optimizations. So in pervasive monitoring, the idea is very simple. If you have the ability to insert an address into a signature in software, and then disambiguate this address against all the accesses that you do, then you are effectively watching this address. Okay, so here's the idea. You would say, I want to watch a memory location and trigger a monitoring function that the user wrote every time somebody touches this address. Okay? And this monitoring function could be checking for an assertion or whatever you want. So you would have something like this. Watch this address. You would have the system call. Watch this address and execute this monitor that the user wrote, okay, every time somebody, stray pointer or whatever, touches this thing. Okay? And so when you execute the system call, then inside the system call, you would have an instruction that says, stuff this address into the signature. Okay? That will put it there. And from now on, keep watching this address. If anybody reads or writes this address, give me an exception, okay, or something. And so you go here, and then suppose that this stray pointer ends up updating this location. Okay? So what this means is that at this point, you get an exception, and you could choose, for example, to execute in a different thread this monitor, which could be, say, an assertion, check an assertion that nothing seems to be inconsistent. Right? So that gives you the ability to watch for a certain location, or a range of locations, or a group of locations, with some false positive, of course. So the first thing you want to do is to check that indeed this is an address that you want to watch.
How do you encode a range into your Bulk filter?
You would then have to have some additional logic. You would have to have, say, a min and a max. Okay? The logic, currently it's very simple, right? It's just an intersection of signatures. But you could think of slightly more complicated functional units that simply check for max and min. Right? Is this less than this and within this limit? And then give the exception. How do you turn off? Oh, very simple. If you have instructions, you can do anything you want, right?
No, you can't take it out of the set because there could have been a collision.
Sorry?
You can't take it out of your set because could have been a collision on wherever it hashed into the set.
Okay, you mean, what if I can take a single address from here, a single one, and keep the remaining, the rest of one, keep them here, right?
You have watch, and now I'd like unwatch or forget.
Okay, so here you have false positives, right? You cannot, from here, you cannot generate the exact set of addresses. So you cannot remove this address from here, right? So you'd have to live with that and do a check every time you do that.
You can do it if you have counters per bit and count down.
You can do that. If you count,
You don't saturate it with the counters.
Yeah, if you complicate the thing, yes. So if you have a counter, how many addresses you have, you can remove the thing, decrease the counter by 1. Okay, compiler optimizations. Suppose you have this new instruction that says begin end collecting addresses, right? So I have a set of code and I say begin collect addresses into a signature. Suppose I have a small register file of signatures, very few, right? And I want to use the signatures to be visible to the software for compiler optimizations, okay? Most ostensibly for disambiguation of groups of addresses at runtime, okay? Ranges, or no, not ranges, sets of addresses. So I can have collect, begin collect, end collect. So what this will do is, at runtime, all these addresses will be put, hash encoded into a signature. Okay? You could say only the reads, perhaps, only the writes, or both in here, right? Then another instruction is begin disambiguate. And the idea is that you say, from now on, start disambiguating against the signature, okay? And end disambiguating. And what this would do is, at runtime, any of these loads and stores will be intersected against the signature, right? And if there is any collision, you can get an exception, or you can set a bit, say, for example, right? That's local disambiguation. You can have remote disambiguation, and what you do is start remote disambiguating against the signature. That means any incoming invalidations or any incoming reads, coherence actions from another processor, let them intersect against the signature. So then, if there is somebody that does some stuff that collides with the signature, you can get again an exception or set a bit. This is very useful, say, for transactional memory, right? So what you would do is you would start collecting, begin collect, end collect. So you'll keep on collecting in your signatures the addresses that you're accessing. And at the same time, begin remote disambiguate. And then remote, you would be watching incoming things that would collide with your addresses, right? So what can you do with this? So I gave an example of transactional memory. Another one would be function memoization. Okay, so you have something like this. Could I eliminate this call to foo? Skip it. So I called it here with a certain input, and I call it again, and suppose it's the same input. Okay, can I just not call it again and just, use whatever I generated last time, even though there are a bunch of pointer accesses in here? Can I do that? Well, I can say begin collect, end collect. Okay, that's going to put all the addresses that this foo is accessing into a signature. Begin disambiguate, end disambiguate. If by the time I get to this point, there hasn't been no conflict, it means that this guy didn't mess up any of the state that this one generated. So I could just skip the call to X if it's the same input. Okay, there's one detail here that is missing. The detail missing is that what if foo overrides a value, right? Then I could not do this. If foo reads something and overwrites it, then I cannot just skip it here, right? Because it had side effects on itself. Does it make sense? So how do I do this? Rather than collecting it into a signature, I collect all the reads and all the writes, and then I intersect the two. And if the two is nil, then I know it doesn't have this overwriting effect. So there's an extra condition to be able to do this. Okay?
This also assumes I do that intersection again with all the other threads that have gone out. There aren't very
Oh, well, so this was a sequential program. If you have a parallel program, then you have to do remote disambiguating. Watch that nobody else messes this up, right? And keep receiving the invalidations for that.
If foo reads and writes the stack, isn't it always going to look like it made a modification to the stack?
Right. So if you mean it writes and then reads the stack, right? If it has a private variable that it writes and then reads, true. So if you do that, then you could skip the second call, certainly. But using the signatures, it would appear that you have a dependence. Correct. Make sense? That's what your point is, right? Fine. So you would not memorize it, but you could even be smarter and say, look, I'm not going to put into this signature this range of addresses that are stack addresses. If it's private stuff, I'm not going to put it into the signature. Someday, the hardware designers will realize that this is very useful for software designers. It's very simple, actually, to do this. Another example is, I guess I mentioned this already, having many watch points. So here you can say, put this address into the signature, put this address, put all the addresses that foo is accessing, and then watch for this thing, if anybody accesses this. Another one, loop invariant code motion. What if, can I move this expression out of this loop? Okay, it would be good because then my program would speed up 5%, for example, right? Well, let me move it out and then collect all the reads, begin collect, end collect, begin disambiguate, end disambiguate, and then check, did I get any conflict? And if I did get a conflict, then I would have to roll back, certainly. Otherwise, I'm done. Okay? So signatures can be used in two ways. One is hit a point, check the signature, and based on that, decide I go this way or this way. That's the simplest way. Or the second one is do something that is unsafe, check the signature, and then decide, oh, what I've done is incorrect. I have to redo it in a different way.
Rollback is kind of a gotcha there.
Is there what you? Well,
Yeah,
you can.
there's a lot of mechanism that you're going to need to be able to roll back.
Okay, so the question here is, yes, you need rollback. So you can use shadow variables, perhaps, right, at the cost of some extra copies and so forth. And or otherwise, don't use signatures in this mode. Use it in the other mode where you do the check first. It wouldn't work this time in here, but do the check first, and then based on that, it wouldn't work in this case here. Right? All right, so you can think of many other optimizations. We're just getting started here. Many compiler transformations rely on runtime disambiguation of groups of addresses. This gives you a nice primitive for this. All right, so to summarize then, what we are after here? Okay, so we're after a machine that has 100 processors, all cache coherent in this case, okay? But you could just have groups of cache coherent processors, okay? Where the novelty is not in the cores. The cores actually can be designed quickly. Take a processor from a company that is your competitor. It doesn't even support your memory consistency model. Shrink it, stuff it there, as long as it supports the bulk, everything is moved to the cache hierarchy. You get high performance. This is completely transparent to the software. You don't need to change the software stack at all. Okay? Signatures are used for disambiguation. Cache coherence, I gave you a glimpse of how it works, but the whole system works with signatures. And then, if you want, even for compile optimizations, the machine supports sequential consistency without any fancy hardware, no snoops, no costly operations in the core. There is room for many new tools that focus on chunks. Okay? For example, as I said before, deterministic replay with no log, data race detection with very low overhead, and pervasive monitoring of this, of watching addresses, and then compiler optimizations if you make the signatures visible to the ISA. That's kind of the high-level view of the project. As you can see, there are many different parts. We're even building an FPGA prototype of this, believe it or not. Each student is working on a different part of this project. There's room to collaborate with Microsoft if there is interest. And I think that many programming and compiler issues remain open. You can see that the emphasis of this work has so far been the hardware, techniques to this, but there is all the software layer that we haven't touched. Okay, so now the next step would be, what if you make some of the stuff visible to the software?
Great, thank you very much. We certainly have time for some more questions if people have them. I'll ask during the talk.
So is your FPGA or basically you start with a single core with this or multiple cores? How are you going to, how much are you going to try to do with your core?
Okay, so this is a very simple core. It's a multi-threaded single issue core in order, right? And so this is a very simple thing. You need multiple of those, right? You just have to chunk them, okay, and have a way of ordering the chunks in the cache hierarchy. Most of the work is done in the cache hierarchy.
Do you think at the end of the day, this is, if you're running a parallel program, this is more or less energy efficient?
Well, so it has some sources of energy inefficiency, right?
And some efficiencies. Do you have a sense for where
So the inefficiency come from, if you have, did you ask sequential code or parallel code?
parallel?
Parallel code. If you have fine-grained sharing, then you run the risk of squashing, right? So that's one of the problems, right? This is where I think most of the consumption, extra consumption will come from. What are the savings? Simpler, no snooping of the core, really. So this part gets simplified. You know, how much simplification, that's an open question, right? But you don't need to snoop things. You don't need to make, invalidations don't have to come up, propagate all the way up. You don't have to log the cache. So that's a major gain. Working with signatures also has an advantage. You don't send individual invalidations, okay? Although the fact that you have signatures means that you invalidate additional locations that you shouldn't, potentially causing extra misses. So some energy is lost from there. Commit is very efficient, okay? All we do is, I didn't have time to talk about this, but multiple chunks can be committing at a time, okay? Updating directories, sending the signatures around, as long as those chunks don't have any intersection. So all the arbiter has to do is to keep in its own arbiter hardware the set of currently committing signatures. And when a new one comes in requesting for commit, simply intersect with all of them. If there's no intersection, you say, okay, you're done, you're committed. And in parallel, do the propagation. So one thing that we're looking very carefully is that this thing should not slow down single thread performance. So there is this arbitration that occurs irrespective of whether you have single thread or multiple thread. This should not slow down the system.
All right, that's it. Let's thank our speaker again, and thank you for the visit.
Yeah, thank you.